All right, welcome everyone. This session is called Innovative Health Data Science Applications. My name is Andrea Lane. I'm an assistant professor of the practice at Duke University, and I work with data science and statistics students. So this session will feature 5 students from either the Duke Department of Statistical Sciences or the Master's in Interdisciplinary Data Science program, and they will present some interesting projects that they've been working on. All right, so let's start with Sonya Eason.
Awesome. Thank you for that introduction. I'll go ahead and share my screen. Okay. Yeah. So my project is geared on predicting provider visits in prisons. So basically what I mean is, like, if we have a survey of prison inmates, we have prison inmate data, can we predict out of these prisons who are actually seeking healthcare help, who has seen a provider since admission, basically. And I think medical history data is an extremely informative part of this. So looking at ways to optimize use of medical history data is the center of this project. So I want to first talk a little bit about my motivation leading up to this. Here I have 2 points, right? And these are 2 points that are in the scheme of like 20K plus data points I have in my data set. And the end goal is to say something about these points and to say, given these other observations we've noticed, we can make assumptions that you are this likely to have seen a provider since being admitted to prison, right? But what really drives me is not just the modeling aspect, but the memory that like, hey, these 2 points are people, these 2 points are people, and people are complex, and that's extremely important. People have different phenotypes, people have different conditions, and that's guiding this modeling process. So I want to give like a little bit of a example that kind of like will help highlight the idea, hopefully. Let's say this blue guy here, we'll call him John, and this purple guy is James. These names are not informative of any person's individual data, by the way. It's not PII, just made this up. Okay, so John and James, okay? We know something about John's medical history. We'll say we know John has hypertension, and we know James does not have hypertension. The other thing we know is that John has seen a provider since being admitted to prison, but James hasn't. Is that enough data? Is that good enough to say, oh yeah, we see an association here? Obviously, these are only 2 points, but it's just to highlight the idea that like it's pretty intuitive that more medical history data should be more informative of provider access. That being said, there's almost sometimes a cost of having more data. So that's kind of what this project is looking at. It's looking at, hey, to what extent do we have a cost of incorporating more medical history data? And is it better to collect more medical history data? It's essentially a proof of concept for the idea that in surveys, maybe we should collect more medical history data. Maybe it is informative of who's accessing providers. So big idea summarized. How much insight can we actually gain into whether someone accessed a provider from their medical history? And is more medical history information better? And when I say more medical history, that kind of is under the assumption that we have information about less common medical conditions and more common medical conditions. And kind of ask the question of like, hey, is having information also about less common medical conditions really informative of actually who's seeing providers? Because maybe it's not, because obviously, aside from medical history, there are many reasons people see healthcare providers. People see healthcare providers as a result of injury from fights or just physicals, things like that. So we could say, hey, actually knowing about less common conditions and whether they occur is actually kind of arbitrary in relation to whether someone actually has seen a provider. So that's the question that's kind of guiding this project. Like, is it important to know about a wide range of medical history? So yeah. So to give some background into the data I was working with data from the Bureau of Justice Statistics, a survey of prison inmates, which, as I said, has over 20,000 observations of prison inmates. And I was specifically looking at medical history data, of course. Here's a few variables that I highlighted here. I actually made these variables by combining the past medical history information available with current status. So ultimately, for each of these variables, we have 3 categories that are possible. Either someone never had the disease, they currently have the disease, or they used to have the disease, right? And other information that I thought was important to include in all of the models as just kind of like a given was gender and race, because demographic information is extremely influential, but also time served in prison. You serve more time, you're obviously probably going to have had more time to see a provider. So that was definitely necessary to account for. Our outcome was, of course, provider, and I saw a pretty decent split between like people who have seen a provider since admission and people who haven't. Significantly more, obviously, saw a provider since admission, but it was enough to make me feel comfortable going forward and modeling this. So now what's the actual process that's kind of like laying behind my experiment? Well, the process is I decided to make 3 categories of models. Models under the framework of, hey, let's have information about the 3 most common medical conditions that are available in this data set, which in this case were asthma, hypertension, and musculoskeletal issues. Okay, and then let's make models with that. And then the second idea was like, hey, let's actually incorporate models that instead have the 3 least common medical conditions. And then the third idea is like, let's make models that have both the least common and most common medical conditions. And if the idea that more medical history, including like those less common conditions that we said could be arbitrary, like what someone may say that could be arbitrary, if that model actually is better, it performs better, it's not as costly to incorporate those variables, then maybe that hints that, associations do exist and that collecting more medical history is super important and super crucial in understanding healthcare access. So within this framework, I built 2 models under each of these categories. For reference, the demographic information and time served was just a given in all of these models. But for each of the 2 models, one was main effects and one was interaction. And the interaction was built in a very like, let's just look at what's significant sort of way, basically fit all possible second order interaction terms and utilize backward selection, and continuing like removing the least significant terms until we essentially were only left with terms that we probably could say like didn't have a coefficient of 0. So yeah. So when we did that, we found, this is an example of one of the models. This was a model that was like this, incorporated all the conditions and utilized interaction terms. So it would look something like this, right? Let me give a correction really quickly. For these, we're expecting multiple categories. So this would be kind of like a sum of multiple terms. So we would have like a beta 5.1 new hypertension currently has it, and like a beta 5.2 new hypertension used to have it, right? With the baseline being like they never had it and they don't currently have it. So same thing would apply to the other conditions, and also in race, for each of the racial groups, there would be a different coefficient and term. Okay, so within the evaluation, I was able to see that actually, like, maybe the concept was proven. Maybe we were actually able to see that having more medical history information was better in terms of predicting provider access, predicting who had seen a provider since admission. Because when we saw ROC AUC and AIC values, they were actually the best for this model, best for a model. So even though it's maybe more complex because there's more terms and probably there's significant interactions, that cost wasn't great enough for the predictive power we had. And that's why we see this low AIC value. And obviously the best AUC is for both, where there's all conditions accounted for. So yes, that was my project. And I'm super excited to continue working on data that predicts healthcare access and also determine modes of surveying populations, because the main goal for me is understanding what data is most important to collect to understand populations. And my argument here is that perhaps medical history data is most important to collect, and a lot of it. All right, thank you.
Thank you so much, Sonya.
Thanks.
All right, next we have Yule Fu. Let me share my screen.
Okay, hi everyone. So my name is Yule Fu. I am a current undergrad sophomore at Duke University, and this is a project that I did over the last summer with an RU program in math and statistics under Dr. Chen, and Dr. Sahu. And it was with the Virginia Commonwealth University. And I also had two more teammates who were also undergrads with me called KDs and Alexander Murray. And so our project was a comparative analysis and uncertainty quantification of machine learning models for sentiment analysis. So our research motivation was trying to use natural language processing and sentiment analysis to look at text responses. So we had a lot of text responses about how COVID impacted VCU students, and then we wanted to see if we can parse out the emotions that were in these text responses and hopefully apply these methods for future surveys and sentiment texts. So the data was collected through the university newsletter during COVID from April to June of 2020, and it was completed by 398 Virginia Commonwealth students. And there was demographics, social networks, mental health, and academic performance that was collected. But most importantly, we wanted to focus on the open-ended question, which was how did coronavirus affect your mental health? And so students were able to freely type in that text box. And so some would give a simple sentence or some would give a complete paragraph. And this data was then manually classified by past researchers into 14 different categories. So we have isolation or loneliness, depression, anxiety, negative feelings, lack of motivation, and so forth. And as you can see, these categories are very specific. And so we want to see if a machine can be able to detect these specific emotions within text. So just a simple breakdown, we can see how often do these emotions appear in these text responses. As isolation appears very often, which makes sense. People often feel isolated during COVID. And then we have depression, anxiety, and negative feelings, and so forth. And we classified emotions that appear very common as major emotions and emotions that appear not that common as minor emotions. And I'll get to why that is important later down the line. But now we use 5 different models to train and to see if they can be able to detect the emotions in text responses. So we have lexicon-based, bag of words, TF-IDF, mental BERT, and ChatGPT. And so now to go into what each one does. So lexicon-based, it is the most simple preliminary model. It generates a dictionary of individual words, which are called unigrams, and it has associative value for a specific emotions. And we use that dictionary to give scores to the text response. So for example, in depression, the word depressed appears very often in people who do have depression. So the word depressed would have a very high score. And so it would, when things are added up together, we would say, oh, if that word is above a threshold, that would be that text response would classify as a student with depression. So bag of words is now a machine learning model. So there is training involved. So similar to lexicon based, it vectorizes the words and it still gives them a score, but each word is weighted equally. And then the machine learning model is then trained on each vector. Next, we have TF-IDF, which is a very similar model to bag of words, except it gives different weights to different words, and it gives more weights to uncommon words. So it's a combined metric of how often the terms appear in the responses, which is the term frequency part, and then the entire corpus, which is the inverse document frequency part. And it just assigns scores to words, and it adds up all the scores within a text response and classifies it. Next, we have MentalBERT, which is a deep learning model, and it can be found freely online. And this was a model that was pre-trained on mental health data that was scraped from Reddit, actually. It's a smaller version of a BERT model, And this data we fine-tuned with also our data, and we expect this model to perform probably the best because it already has pre-trained data from before, and we also train it with our data. And it's all very mental health specific. And finally, we use ChatGPT, and it's very similar to how you would use it on your web browser. So you give it a prompt, and our prompt was you're categorizing the emotions and issues expressed by the students. And then this would send it to the OpenAI API, and it would classify it. And in this research, we use 3.5, but since now there's also 4.0 and 4.0 mini, we might be able to test those out and see how well they do. And then we had 2 stages, but stage 1 was just general testing comparisons. We had a 20-80, 80-20 testing and training split, no cross validations. And then we had the confusion matrix with the accuracy, precision, recall, and F1 score for each model. And then we did it for each emotion. So for example, for the category of depression, so we fed it for each model and see if each model can correctly predict if each student has depression or not. And as you can see, lexicon-based actually performs the best with a 99% accuracy and F1 score. However, for a minor emotion such as financial stress, so financial stress is not a lot of people exhibit financial stress within our entire data set. And also financial stress is a lot harder to discern based on the text. So we can see that GPT actually performs the best in terms of F1 score as well as accuracy. So stage 2, we did an uncertainty quantification. So we tested all the models again on the 80-20 split, but we used a 5-fold stratified cross-validation. And we did the same thing with collecting the confusion matrix. And we also generated an ROC curve for each model and for each emotion. And so as you can see for the ROC curve for depression, lexicon-based again performs the best. Out of TF-IDF bag of words. We didn't put MentalBERT and GPT because they're deep learning models and they're also pre-trained. So you can't do ROC analysis with that. And then so for another minor emotion, which is negative feelings, you can see these models perform similarly in terms of ROC analysis. And so here's just like a basic summary. So we found that lexicon-based, it performs very well on major emotions. So emotions that occur very often, and that's probably because you have a lot of data to train it on. And that is similar for bag of words and TF-IDF. However, when you don't have a lot of data to train it on, lexicon and bag of words and TF-IDF, they perform more poorly. And that is when MentalBERT and GPT, because they're pre-trained models, they would perform better. However, it is more computationally expensive. And so for uncertainty quantifications, again, similarly, it is better for lexicon-based and bag of words to understand emotions in text that you can train it on you can train it on data that has occurred a lot on major emotions. However, in MentalBERT and GPT, it works better also on minor emotions. However, across the charts, we found that MentalBERT performs relatively the best because it was pre-trained as well as it also has fine-tuned with our data. And so acknowledgements, I want to thank National Science Foundation and the VCU and also Duke University for allowing me this time to present at this conference. So thank you.
Thanks so much. Great. Next, we have Caitrin Murphy.
Okay, I'll share my screen. Okay. Hi, everyone. Today, I'm going to be talking about some methodology development and also an application in functional principal component analysis in the case where the functional trajectories are actually truncated because of a device they're measured on. And this is joint work with Eric Laber, Brian Reich, and Rhonda Merwin. Okay, so I was first introduced to the concept of truncated functional data when we were asked to analyze some data from Rhonda's clinical study, and that's going to be the running example for the next few minutes. So her overarching objective was to predict eating disorder diagnoses in type 1 diabetic patients using their glucose behavior. Now, there is what's referred to as the gold standard diagnostic tool for eating disorders, and it's a questionnaire. However, it's not really tailored to diabetic patients because there are some questions like, were you hungry every time you ate? A diabetic patient might answer no, but really they only ate because they were experiencing hypoglycemia symptoms and not necessarily eating disorder symptoms. So the purpose of this prediction problem is to give clinicians just another metric to use when diagnosing eating disorders. So back to the study, when patients were enrolled, their demographic information was collected, everyone took the EDEQ, and then they were given continuous glucose monitors, which measured their blood glucose trajectories over time. So this is our functional data. And this is the black curve we're seeing on the graph at the bottom. And they're also asked to report meal times, and those are the gray vertical lines. So there's a natural spike in blood glucose post-meal. And this is an example of someone with just type 1 diabetes. However, if someone also has an eating disorder, these trajectories typically show up as much more variable and also have prolonged elevated glucose levels. But we don't always get this information because our monitor only supports glucose values between 40 and 400 milligrams per deciliter. So instead of getting to observe what we'll call Z, which is the black curve, the patient I's true blood glucose, we see W sub I, which is the CGM data. It's a little noisy because of the measurement error, and it's also truncated at 400. So if you see around 8 p.m., you get a cutoff of the real process. So to make this a little more formal, we're going to allow Z to represent the true underlying blood glucose process, and we're going to assume it's an L2, and it has continuous mean and covariance functions mu and sigma respectively. So we can actually represent our CGM data, which is W, as the sum of a realization of the true blood glucose, C sub I, plus a little measurement error, which is represented by epsilon sub I, which is a Gaussian white noise process, scaled by sigma, which is just the measurement error standard deviation. But we're also truncated to that 40 to 400 region, which we'll write generally as A to B. So that's where the max and min come from here. So in total, we observe data that are composed of our truncated functional trajectories. We have baseline covariates as well. And then we have our outcome of interest, which is a binary indicator of eating disorder status. Okay, so now the goal becomes, how do we represent this infinite dimensional functional process as the sum of components that we can actually estimate? And what we'll do is use the Karhunen-Loew expansion, which allows our process Z sub I, so for unit I, their unobserved glucose, at time t, to be represented as a mean function at time t, plus an infinite sum of FPC scores times their eigenfunctions. So an FPC score here is just the integral over the time domain of the centered function times the eigenfunction. And this is a standard definition. So we want to be able to estimate all of these components, and what we'll do is modify kind of the traditional FPCA steps to account for truncation. So we're going to, in step 1, construct estimators of the mean and covariance functions. Then we're going to propose an FPC score estimator. And then finally, we're going to posit a generalized functional linear model using those scores to take us back to our classification of eating disorder problem. Okay, so I just copied and pasted the form of our observed truncated data here. And just for notation, we'll let this Z plus sigma plus epsilon sub I be denoted by W tilde. So this is just, it's the untruncated process, but with the measurement error. So we can notice that W tilde, the variance can be represented in 2 components. So it's equal to the variance of the underlying process C plus that measurement error variance. So if we want to derive estimators of our mean function and our variance function, we can actually maximize a local kernel weighted likelihood. So here in this term, we have our kernel A sub h, where h is just the bandwidth. And this allows us to borrow strength across time, which is helpful in cases where the trajectory is more sparse. And then there are three contributions. So delta to the A is just an indicator. So we'll take on the value 1 if your point is truncated at A. And then probability of being truncated from A. And then we have a contribution from not being truncated, and then a contribution from being truncated above at B. So maximizing this quantity yields the estimator for the mean function and also the diagonal of the variance plus measurement error variance function. Okay, so the next steps are to estimate the off-diagonal elements of the covariance function. And very briefly, we can do a similar local log likelihood maximization procedure, but this time with a bivariate kernel. And we'll use projected gradient descent to maintain that positive semi-definite structure. And then the last step here is to actually construct a predictor for the FPC score. So we're going to take on a similar approach that Yao et al. Did in 2005. And we're going to define C star as the K FPC score for unit I. And it's just the expectation of the true score conditional on the data. So it's the best linear unbiased predictor. And it turns out that this is equivalent to first conditioning on the untruncated noisy process to get this closed form expression here, and then conditioning on the data. So what's nice about this is that all of the components inside the expectation we have available from the previously constructed estimators. The only part that's missing is this W tilde, but we're able to sample it conditional on the data from a truncated normal distribution, plug it in, and then take the sample average, and that's our estimator. And then once we have these C stars, I won't go over the functional model, but you can think of them acting as covariates and then using a standard regression technique. So in this case, logistic regression, and our FPC scores are treated as covariates. So going into some results, on the top left, we have plotted some of those blood glucose trajectories. So the light gray is for those eating disorder patients. The dark gray is for non-eating disorder patients. And then we have our smoothed mean function in red. So overall, we see that the eating disorder people are running much higher on average. They have those truncated trajectories at 400. But overall, we see a glucose spike, and then about 75 minutes later, it tapers off and stabilizes. And then on the right, we have our smooth covariance surface estimate. The main point here is that those first 30 minutes post-eating have really high correlation, those glucose values, and then it tapers off as the lag time gets larger. And then finally, for model diagnostics, we considered two other models. So we have our functional model, which consists of all the components I just talked about. And then we also regressed on just the average blood glucose and no blood glucose at all, everything with baseline covariates. And we saw that the functional version performed better in terms of accuracy, residual deviance, and AIC. So that wraps up my project. Thank you everyone for listening.
Caitrin. Next, we have Carol Wang.
Hi everyone, let me share my screen. All right. Yeah, so I'm very happy to present my work on the tree-based generative models with applications to microbiome compositional data. And also, I do want to mention this is a joint work with a lot of awesome people, including my advisor at Duke and also our previous Duke Stats alumni. So the data that we're looking at and some context about it is that, I'm working with the human microbiome data, which is the collection of the genetic information of microbes that reside on or within the human body. And why is it important? So studying the microbiome provides insights into various aspects of human health. And traditionally, people are more interested in, for example, cross-group comparison of when we have a case control study, how are the subjects in the case group have different microbiome profile from the people in the control group. But recently, with the development of the generative models, simulating the microbiome compositions of the group of individuals that satisfy certain condition can actually be of practical interest. So this is a very new area. So all of the work here are like some first attempts to build data synthesizer for the microbiome compositions. Okay, so what does the data look like? A typical microbiome data set contains those three components. The first part and the most important part is the OTU table, which is a count table as shown here. Each row represents a sample that is collected in the microbiome study. Each column is an OTU, which is a unit of the species. So those counts form the basis of the human microbiome analysis. And we aim to build generative models to generate those counts. And the second part is the phylogenetic tree, which is a binary tree. And the leaves of the tree are the OTUs we see in this OTU table. This tree encodes the evolutionary relationship among the OTUs. And hopefully, it's also a proxy of the functional relationship of the OTUs. And finally, it's very common to have some design features in the studies, including most commonly covariates, and also sometimes we have like longitudinal sampling. Those are also things that we want to account for when building data synthesizer. So why is this a challenging task? This is mainly because of the characteristics that the microbiome counts intrinsically have. So the data is compositional. The OTU table is compositional counts, meaning that so the total counts here, which is summing up each row, is actually doesn't represent any how many bacteria is in that sample, is a experimental artifact. And also this data is high dimensional and is very sparse, meaning that for each row, for each column, we both see a lot of zeros in the OTU counts. And finally, the samples exhibit very large variability and there is a very high cross-sample heterogeneity. So the existing works are mainly trying to address those characteristics and also the existing work are mainly focusing on, for example, differential abundance analysis, or trying to build some predictive models for, let's say, disease status, right? So we're aiming for something more generic, that is to have data synthesizers so that we can have a better understanding of what is the typical profile, a microbiome profile of some subjects under certain conditions. So I'm going to introduce two classes of models we have built. The first one is a single tree model utilizing the phylogenetic tree that is called the logistic normal model. So the idea is that since we have count data, we can decompose the count. We can decompose the count generating process by along the phylogenetic tree, so that we model the count distribution at each node as a binomial model, and then for the binomial probabilities at the nodes of the phylogenetic tree, we assume a latent Gaussian representation of those. So we take the logit transform of those binomial probabilities and assume that those log odds are jointly multivariate Gaussian. So why is this useful? This allows us to first make the data less sparse by aggregating the counts along the tree. And second, with this multivariate Gaussian representation, so we can actually use all of the very mature tools that have been developed for multivariate Gaussian analysis and apply them directly to this data. And also, it's as mentioned before, it is important to be able to incorporate the design features such as the covariates and the longitudinal sampling. And we do this by using a mixed effects model, basically linking the log odds with the covariates. And given this basically multivariate generalized linear model formulation, we can also do commonly useful tasks like two-group comparison. Let's say comparing the microbiome compositions between the case and control subjects. So let's skip the technical details, and by imposing a spike and slab prior on the coefficient of the case control group indicator, we can actually do hypothesis testing along the tree. And also, as we can see from this model formulation, given a set of covariates and the grouping structure of the samples, this is a fully generative model. So we're able to draw samples like fake data, synthetic samples from this model. So from the hypothesis testing perspective, we demonstrate that through a case study where the data is from the Diabetic project, where 777 samples were collected from 33 infants. This is a longitudinal data set, and we aim to test whether there is change in the microbiome compositions after seroconversion. And with this formulation, what we get here is that we can visualize the cross-group difference between case and control on this tree. So here, as we can see, some nodes have a higher PMAP, where PMAP is just the posterior probability that there is cross-group difference at this particular node. So this helps us to target the group of taxa that shows cross-group difference. And now that we have a pretty good single tree model, the next step is to actually borrow the idea from the more classical machine learning models, which is to do ensemble. So the methodology of normalizing flow actually allows us to do the tree ensembles if we properly choose the class of transforms in the normalizing flow. So the formulation is like this. So we have pairs of data. As mentioned before, it would be covariates and composition. And we just aim to use conditional normalizing flow with trees, based on trees, to model the distribution of the composition of the microbiome composition given the covariates. And by doing this, by utilizing those more flexible nonparametric generative models, what do we get? So going back to this Diabetic example, we just see still using the same set of covariates and the same outcome, which is the relative abundance of the microbiome composition, projecting the real data and the synthetic data we generate from these two classes of models to a lower dimensional space. We can see that, okay, the first row is the real data. The second row is what we get from this conditional tree flow, which is the nonparametric tree ensemble. The third row represents synthetic data generated from the logistic tree normal model, which is the single tree model. And each point represents a sample, and they are colored by age. So we see that the trend and the trend of the microbiome changing with age and the association with age is preserved in both types of model, but we also see the potential of the nonparametric models. So as we see that the synthetic data generated from the nonparametric normalizing flow actually are more closer to the real data. So however, it is more challenging to incorporate other design features like the longitudinal sampling into the nonparametric machine learning models. So those are the two classes of models that we have considered for microbiome data generator. And this concludes my presentation. Thanks all.
All right, thank you so much. So finally, we have Tina Yi. Tina, are you there? Okay.
Hi everyone. Can all of you guys see my screen?
Yes, all good.
Cool. So hi, my name is Tina, and I'm currently a master's student in the interdisciplinary data science program from Duke University. So here I present our research on examining the impact of image preprocessing on diabetic retinopathy detection across dataset analysis with various camera sources. So this research is conducted by myself along with my teammates, Afra, Wang, and Danny. Oh. Okay. So diabetic retinopathy, or the so-called DR, is a serious health issue affecting millions around the world. And it is nowadays the leading cause of blindness, especially in low and middle income countries. So it generally hits people during their prime working years between 20 and 74. So in 2019, the World Health Organization has reported that there's around 422 million people worldwide are living with diabetes. So it put them at high risk for DR. That's why early detection is very important. So catching it early can prevent blindness and overall improve the lives of millions. That's kind of the goal of our research. We want to focus on creating effective and accessible screening methods to help address this urgently. So here are several stages showing the progression of DR. So here we can see that at stage 0 or no DR, the image shows a healthy retina with no visible lesions. Moving on to stage 1, the so-called mild DR, we begin to see some microaneurysms or MA. So these are small areas of balloon-like swelling in the retina's tiny blood vessels. And then we move on to stage 2, the moderate DR. At this stage, we observe both microaneurysms and up to 20 small hemorrhages, or the so-called HM. So this stage signals the disease is advancing. And then here at stage 3, the severe DR, we can see that the image shows more than 20 hemorrhages along with other microvascular abnormalities. So damage to the retina is becoming more extensive. Finally, we have the stage 4, which is the proliferate DR. This is the most advanced stage. Here we can see the neurovascularization, which is the growth of the new and abnormal blood vessels. And we can also see the pre-retinal hemorrhages. So this stage poses a higher risk of vision loss. So currently, the retinal image analysis can be automated thanks to the advanced machine learning models, but there's a key challenge here. So the variation in image observed by different types of cameras can limit the model generalizability. That means that it can impact the model's performance. So our research focused on developing more robust models that perform consistently across diverse imaging equipment. So it can help to make it more practical in real-world healthcare use. So our research hypothesis is that image preprocessing can lead to more generalized performance of DR detection models across diverse datasets. To test this, we utilize 3 distinct data sources. So the first one is that it's called Macedor. It has approximately 1,200 images. The second one is IDRIT. It contains about 550 images. And the last one is DDR. So DDR is our largest dataset. It has around 10,000 images. So as you can see from the sample images, each dataset has its own unique characteristics in terms of color profile, contrast, and field of view. So it provides an ideal testbed for our pre-processing techniques. So our research methodology builds upon the paper published in 2022 called Diabetic Retinopathy Fundus Image Classification and Lesions Localization using Deep Learning. So we are using EfficientNet B0, a pre-trained convolutional neural network, as our model architecture. So our approach has 3 key steps. So first, we validate the model using transfer learning on the DDR dataset. And next, we establish a baseline using raw images from Macedor and IDRIT datasets. And finally, we evaluate various preprocessing techniques, both individually and in combination, to assess their impact on model generalizability. So our study explored 3 key image preprocessing techniques. They are cropping, image enhancement with noise removal, and color normalization. So cropping focuses on the most relevant parts of the retinal image, and IENR improves image quality and reduces noise. And lastly, color normalization standardized color profiles across different datasets. So we use EfficientNet B0, which is a pre-trained model known for its very good performance on ImageNet dataset. So we applied transfer learning techniques to customize this model for our study. So here you can see that we adapted the model for our detection test by replacing its top layers with a custom configuration. So it includes the global average pooling layer, 2 fully connected layers, and a softmax layer. So here is our single preprocessing pipeline, which begins with resizing raw retinal images. And then we have 4 parallel processing streams. So the first processing stream is a baseline with no additional preprocessing. The second one is image enhancement and noise removal. The third one is cropping and resizing. And the fourth one is color normalization. So we can see that each stream includes data augmentation before feeding the processed images into the EfficientNet B0 model. This approach allows us to systematically evaluate the impact of individual preprocessing techniques on model performance. And here we can see our multiple preprocessing pipeline, which combines different preprocessing techniques in various sequences. It includes pairwise combination and a combination of all 3 methods. So this approach allows us to evaluate how different preprocessing combination impact the EfficientNet B0 model's performance in DR classification. So it can potentially reveal some synergistic effects between preprocessing techniques. So here we can see the evaluation performance of models trained on the master dataset using various preprocessing methods for DR stage classification. Yeah, I was just clicking on the comments. Okay, back to the slides. So here's the evaluation performance of models trained on Macedor, and the x-axis shows different preprocessing techniques, while the y-axis represents the accuracy percentage. So the blue bars represent the model's performance on the Macedor dataset, which the model is trained on. And the orange bars show the model's performance on the IDRIT dataset, which demonstrate how well the model generalized to a different dataset. So the dashed blue line at 58% indicates a baseline accuracy for Macedor, and then we can see the dashed orange line at 46% shows a baseline for IDRIT. So looking at the results, we can see that the IENR slightly decreased performance for both datasets. And cropping alone significantly improved accuracy, reaching to 67% for Macedor. And unfortunately, color normalization on its own didn't offer much improvement over the baseline. And then we tested various combination of this method. So the standout performer is cropping plus color normalization. It boosted accuracy from 58.3% to 17.8% for Macedor. So this combination generally showed the most significant improvement in our study. And a key observation here that I want to highlight is that we can see that the model consistently performs better on Macedor compared to IDRIT across all preprocessing methods. It indicates that the choice of training datasets significantly impacts the model's ability to generalize, as we already expected. And then move on to the next visualization. It shows how the models trained on the IDRIT dataset performed in classifying DR stages using different preprocessing methods, both on their own and in combination. So the orange bars represent the performance on the IDRIT dataset, which is also the training data. And the blue bars here shows the model, how the model did on the Macedor dataset for generalization. So one standout here is cropping. So we can see that it boosted accuracy on IDRIT from the baseline of 62.5% to 66.7%, which make it become the most effective single preprocessing method. And again, the choice of training dataset plays a big role in how well the model generalized, as a model trained on IDRIT consistently did better on its own compared to Macedor. So based on the research results, we can conclude that the choice of preprocessing technique can significantly impact the performance of DR detection models. So we can see that the image enhancement and noise removal consistently led to poorer performance compared to raw images. It is possible due to the smoothing of important lesions like microaneurysms. And cropping shows to be the most effective standalone preprocessing method. It is likely because it reduces the effect of field of view differences across cameras, and it helps to eliminate non-informative black pixels. And lastly, while color normalization alone decreased performance, the combination of cropping and color normalization has the best results overall. So this synergy works so well, likely because cropping helps to cut out the black pixels that would otherwise interfere with the color normalization process. So in general, our research helps to improve diabetic retinopathy detection by developing models that generalize across diverse datasets and camera sources to help enable the early screening and timely intervention. And future research will focus on improving pre-processing techniques like image enhancement and noise removal, while also exploring model generalization across diverse datasets and cameras. And we also aim to apply our findings to other models and metrics. We want to extend the impact beyond diabetic retinopathy detection in medical image analysis in general. And thank you so much. That concludes my presentation.
Thanks so much, Tina. So we do have a few minutes to spare. If anybody has any questions, you could use the Q&A or the chat. For any of the speakers. Thank you so much, everybody. We'll leave a few minutes for a break. All right, thank you.